Welcome back to the high performance engine building classes. Today we're going to talk about oiling systems. Now, this is going to be everything about talking about picking up the oil out of your oil pan, or in case of a dry sump, a tank, and pumping it through the entire engine and it getting back to the pan. So, we're going to start out with the fact that we've got a couple different versions. We've got what's called a wet sump and a dry sump. So, our wet sump is your typical oil pan at the bottom of the engine. That's where all the oil is stored. And a dry sump is going to be when you store it remotely in a tank away from the engine itself. Almost every production car ever built is a wet sump setup. There are very few that have a dry sump setup from the factory, but there are a couple of Corvettes and exotics. And so, Corvette one's kind of like a weird hybrid sort of a thing. But we're just going to stick to the typical wet sump and dry sumps in this video for a topic. Now, with a wet sump, the way we're going to start out is with our oil in our oil pan. So if we're just going to draw a typical, actually, you know what, I should draw this the other way, that we've got plenty of space. So we're going to have our oil pan, and then we've got all of our oil down here in our oil pan. We need to get that to go through our engine some way, so we're going to have an oil pump. If it's a regular rear mount distributor type V8, maybe some of the ones in the front also, it's going to start with the fact that we've got our camshaft running through our block. And we got our distributor gears that are then driving a shaft that comes down in and into the oil pan, where we've got a pump with a couple of gears in it and a pickup tube that then goes down into our oil down near the bottom of the pan. Now, this needs to be a certain distance away from the bottom of the pan, and that is to have the proper amount of clearance in here so that, number one, we don't suck up the bottom of the pan and it cut off oil flow, or that we're too far away and when the oil gets low we suck air. So this distance needs to be set. It's typically around 1/4 to 3/8 of an inch. Depending on your oil pan and pump and pickup manufacturer, they might or should give you a number for what that is. 3/8 is kind of on the wide side in my own opinion, and 1/4 inch is a good place to target. Anything that's like an 1/8 inch is probably way too close, unless there's like some little buffers on the bottom of your pickup that will actually stop the pan from sucking up completely tight. However, not all pickups come with that. This is a very, very important thing to check. Whether you got to put clay in there or you put a straight edge across the top of your pan and measure how deep your pan is, and then you put that same straight edge on your pickup and you measure to your oil pan rail on both sides of the block. If there's an angle to it, you can average those two numbers to get what the middle is, but you need to check that, because if you don't, you can end up with oil starvation and take out the entire engine if it's done wrong. Now, as our oil travels through the engine, it's going to get sucked up into the pickup, go through the tube, and up through the gear set. Now, these gears are turning in a way that they can pump oil around the outside and push it into an oil galley that then goes up into the engine block. Once in the engine block, typically it'll be rerouted over to an oil filter. All the oil's coming in, going into our filter. You know, so it's all the way around, gets filtered in, comes back up and back into our engine. Now this is where things change a lot depending on the engine. It's different based on how the engine was manufactured, whether it's a priority main type of block or not. But we really don't need to dive into that. Priority main just means that the oil goes to all of the main bearings first before it goes up to the camshaft and lifter galleys in a typical V8. And that's just based on the design of the block. Like aftermarket Dart small block Chevy blocks are designed this way, where it has to go past all of the main journals first. So it starts at the rear of the block, goes to the front before it goes up to the cam. So in my typical Oldsmobile stuff, it does not do that because it comes back from the oil filter, it goes up and runs down a lifter galley first. So it feeds the mains as it goes, which then feed the cam, but it's also feeding all of the lifters on one side of the engine, which is feeding ahead before it gets to the front and goes down to the last main and then over to the other lifter galley to feed the other side. So that is a not main priority engine setup. Just small nuanced differences between different blocks. Nothing really big. Well, let's pretend this one is a main priority. So we're gonna end up probably around where the camshaft bore is. Let's just draw a cam in here to visualize this. You know, so we got our camshaft, got some journals on it. You know, and we got our crankshaft journals down here too. So we're gonna feed it down one oil galley. Now if it's priority main, it's going to be shooting down to our main bearings as it goes. Then it will be fed up and then come back where it can be feeding our cam from up here, or typically it'll actually be V'd off where our mains then feed the camshaft journals since they're directly above it. But then when it's up here, now it's going to be feeding all of our lifters going up to the head as we go along. You know, or depending on if it's overhead cam style setup, there'll be somewhere in here where it goes up to the head too. But basically, you know, once it fills these lifters, it goes up push rods to the head. Like there's a way it's getting to the head on every engine. Once it's up at the head, we need to drain it back, which can be through the push rod holes, and it just kind of waterfalls and finds its way back into the oil pan. Or we've got, you know, like specifically drilled drainage holes that then kind of feed all the oil back to the front of the engine, and it drops down and then drops down and into our pan again. This pan is drawn kind of short compared to where I put everything, but we don't have to worry about drainage back from our camshaft and our mains because it's just kind of flying everywhere. And what that happens is it ends up with this big like oil mist. So there ends up with just like an entire oil mist everywhere here in our crankcase. And that oil mist makes drag because the crankshaft is trying to spin inside of there, the rods, pistons, everything. And that oil mist and getting rid of it is why the dry sump is something that we need to talk about. So dry sump works in a similar way, except we have a pump. Now, the pump can be driven directly off of, say, a camshaft at the front of the block if it's mounted facing off the front, or it's driven by a belt off of the front of the engine. Now the pump has what are called stages, so that's different sections of it where we can either pull oil in or push oil out, kind of a thing. Now in a dry sump setup, our oil starts off in an external tank. We're going to come off the bottom and go to our, we're going to come off the bottom and go to our pump. And then our pump's going to create pressure, which we'll send back to our oil filter. And then it comes off our oil filter and goes into our engine. Now once it's in the engine and it's fleeing off of the crankshaft and everything else, we're going to start filling up this oil pan, except we don't want to fill it up. We're actually going to have some ports in our pan to suck it out. And what those are going to do is we're going to be sucking out the oil and going back to our pump. And there'll also maybe be a couple of draws off of the valley area. So same thing, we can be pulling that back to the pump. And what this is doing is this is creating a vacuum inside of the crankcase, which is sucking all that oil mist we were talking about out, which is reducing the windage drag of the rotating assembly spinning in all of that oil mist. A good example for this would be, think about your car going down the road when it's raining really hard. Like, you may not notice it, but all of that water hitting your car and having to be your car trying to drive through it is making drag. And we're trying to eliminate that in our crankcase because we're obviously talking about way higher speeds than a car just going down the road when that crank is spinning. And once it comes back to our pump, we're sending it back to our tank, either in separate lines or one condensed line, where it can kind of like swirl and evacuate any air, and it's got plenty of time to recondense into solid oil. So the benefits of this, beyond just getting rid of that windage, are then pulling that vacuum in the crankcase, because that lack of crankcase pressure, as we talked about in the previous video, with our piston and our rings. Well, when there's a bunch of crankcase pressure, that pressure is trying to push up on the ring. So if we got our piston ring, and our piston, and if there's crankcase pressure coming up past the piston and pushing up on this ring, it's going to leak, and we're going to lose power and make artificial oil blow by. It'll end up pushing here, pushing the ring in, and then it's just shooting past up into the combustion chamber. Just all kinds of undesirable things going on there. We'll burn oil, it'll lose power. There's just, we don't want that to happen. So by pulling a vacuum, we're going to have our cylinder pressure pushing down. It's going to be sealing the ring, as well as there being a suction down that's sealing the ring. So now we've got everything working together to keep the piston ring sealed, and we will gain power because of that as well. Now, I've done not even a full dry sump comparison in back-to-back dyno runs, but I have done vacuum pump comparisons. So a vacuum pump on a wet sump will make the crankcase pressure go down. It's not solving our windage issue though, because there's still oil gathered in the pan. But we are adding a vacuum to help with the ring seal. And on roughly 500 horsepower engines, that I've done this on 3 different engines on 3 different brands. One was a 5.3 LS, one was a 347 stroker small block Ford, and one was a 340 Mopar. So all sub 350 cubic inch. They were all making around 500 horsepower before a vacuum pump, and they all gained 30 horsepower from the vacuum pump, give or take 2 or 3 horsepower. And that was just from better ring seal, because it wasn't because of the windage. So in a dry sump application, we're getting rid of the windage also, and we're going to gain at least 30 horse, if not more, because we're reducing that windage drag. But where the dry sump really comes in is, we were talking about the oil pickup issues that you might have. Well, assume we did everything right there with the wet sump. But now we take a corner like on a road course. Oil starts sloshing, or we're up high in the RPM and the oil's not draining back from the cylinder heads fast enough because it's relying on gravity and draining back against the crankcase pressure. Because if you've got little drain back holes or areas where the oil has to drain back, but you're high in the RPM and you've got a ton of crankcase pressure, it's going to kind of hold that oil up. And it won't be draining back fast enough to get back to your pickup. And you're going to lose oil pressure if that happens. The difference with the wet sump or the dry sump here is that we've always got a reservoir of oil in our tank that is then directly fed to our pump, directly to our filter, and back into the engine. Unless you're low on oil, this won't change, because as soon as that oil gets pumped through the engine, comes off of the bearings, or wherever it's lubricating, the lifters, the camshaft, crankshaft, wherever it's coming off, the vacuum that we're pulling in the crankcase is immediately sucking all of that oil back out, along with enough air to make the vacuum, putting it in the pump, putting it back in the tank. So it doesn't matter if we're taking high G corners or what RPM we're at. As soon as that oil is free of the oiling system, or oil galleys rather, and the bearings in the crank, it's on its way back to the tank. We don't have to wait for it to drain anywhere. We don't have to wait for it to do anything. It's being pumped back. And that's why when you see road course cars or really high-end sports cars that are meant to have a ton of G load and corners and stuff, they're almost always using a dry sump setup because they have to, because the only way you'd be able to get a wet sump to survive with that is you'd have to have an increase in the volume of stuff, of oil in that oil pan in order to have the reserve built up. The problem is if we look at it from a front view and we've got that oil sitting in here and you go into a high speed corner, that oil is now going to redistribute itself to the side. And if your oil pickup is here, you're now at risk of sucking air because of where it's positioned. Now you can add trap doors in the pan, which is like, honestly, I don't think any oil pan should come without trap doors, or you shouldn't be buying one without trap doors. Most drag race style pans only have one that's front to back in the oil pan, and that does absolutely nothing for you if you're taking a corner. I personally refuse to spend money on any of those pans. I will only buy a pan if it's got multiple trap doors, which means it's got one at the front of the pickup and it's got one on each side of the pickup to make sure that the oil gets there, and then if you're cornering, that trap door Here, draw it down here. So we've got trap doors on hinges so they can swing open if we're cornering and the oil is going that way, but this one stays closed because the oil is holding it closed, or vice versa in the opposite direction, kind of a thing. And then these little compartments are mostly closed off. They've got small holes in them for drainage in to fill them up. But then when you corner, it'll open up, let that oil out to get to your pickup in here to supply oil. And that doesn't even always keep you covered. So if you are using a wet sump and you are going to be taking some corners, but maybe not so like race car aggressive that you need a full dry sump, you can get by with an AccuSump for a little while. Now an AccuSump is going to be a remotely mounted reservoir again, but we don't have oil stored in it. All the oil is still coming from the wet sump pan. But there's a piston in here that's got some O-rings to seal it off. And the oil will come in and fill as the oil pressure comes up after you start the engine. And that will fill this cylinder. There's just a little bit of air pressure on this side, so that it will fill it up, compress it, and then if your pickup sucks a little air and loses oil pressure, this piston will then be forced back in and push oil back into your system to maintain oil pressure. And that only works to a certain degree. I have actually run to the point where my full trapdoor wet sump and a 3-quart AccuSump, so I went from 6 quarts in my oil pan and added another 3 quarts into the engine, and still see my oil pressure come down in some big, long, extended corners. And that was when I knew I needed to switch to a full dry sump setup on my race car, because I just could not keep the oil pressure maintained. I mean, I kept it above 0, but when you're still going full throttle through a corner and your oil pressure gets cut in half, it's not a great sign. And while it lasted and it managed to keep the engine from being damaged, it was not something I was willing to count on long term. So there are things you need to think about with the design of the oil system itself. Pressure versus flow. Now this is something that gets talked about quite a lot, but I don't think most people really understand in a way that's actually worth knowing for building an engine. And this comes down to there's multiple ways to adjust both of these, but unless you're planning ahead to figure it out, you don't really understand what's going on. And granted, there's going to be almost most applications where it just doesn't matter to most people, because they're never going to get into a situation where they're going to actually have a problem with it. So let's clarify what these are. So flow is going to be the amount of oil that is being pumped that by the pump, but is also actually able to go somewhere. This is going to be flow, and that's going to be measured in a volume. Pressure, by definition, is going to be, pressure is going to be the resistance of flow. So if we think about it in a supply and demand type situation, more supply than demand is pressure. And flow is going to be the demand by itself. Because that's how much we're using, and excess of that is going to be pressure. So we start with our pump, goes into an oil galley, goes to the filter, goes back to the oil galleys and bearings, etc., wherever we actually need our oil to be at. So their galley is our first possible restriction point. Filters are another restriction point. Then we got more galleys that are restriction points, and bearings should be our final restriction point. So these restrictions as we go are restricting the flow, and therefore what are creating the pressure. Because if the pump spins and it's not hooked to anything, it won't create any pressure because it's just making flow. There might be just a tiny residual if you want to get real scientific about just internally in the pump making pressure, but the point is that we have basically, if we don't have any of this, we have zero pressure if we just got a pump. We have lots of flow though. And we need pressure at the bearings to make sure that we can support the parts that are turning. And to give a good visualization of that, we're going to have our crankshaft is spinning, and we're going to have our block and main cap. Now we're pumping in our oil to our bearing here, and the goal is to have a layer of oil always supplied around that crankshaft and the bearing. Now how it escapes is out the sides. So we've got our bearing, and our crankshaft, so that oil is being fed in, and it's sitting here in between them. Well, it escapes out the sides as it's being used. So we need pressure to hold this up, because basically if you think about it, you're trying to lift the crank off of the bearing and keep it supported in there. Well, the oil needs to flow also, because we need the flow, because if this oil was in here and it was a sealed system and we had no flow, it's going to cook that oil, because there's going to be a little bit of friction in there all the time, and friction builds heat and it will burn that oil out. So we need the pressure to support the parts while they're turning, and we need the flow to keep them cool and to keep the oil itself cool. So when we have a gap of, say, 2 thousandths versus 3 versus 4, and we're just gonna supply our oiling system with X amount of flow, and that happens to create Y in pressure. Well, we have a fixed amount of flow out of our pump, and at 2 thousandths clearance, it's going to make A for pressure. At 3, it'll make B for pressure, and at 4, it'll make C for pressure. Now, I'm just making these up because we're talking about the concept right now. But if we have say A is 50 psi at 2 thousandths oil clearance, so that's what our Y is becoming. Well, at 3 thousandths of clearance, it might only make 45 psi. And at 40 thousandths of clearance, it might only make 30. And the reason is because this gap is getting bigger, and therefore it's letting more flow. So flow goes up, pressure has to go down. And this is also assuming we are not on the bypass spring in our pump. But if we are on our bypass spring in the pump, so let's say our bypass spring is at 50 psi, that's why we're making 50 psi here. So it's still going to be 50. Well, at 3 thou, we might still make 50. And at 4 thou, we might make 45. And that's because the oil never gets into the system. It goes to the pump, it hits the bypass spring, and it just dumps back into the pan. It never makes it through the system to begin with until we increase our flow by increasing our bearing clearances. Then it starts flowing through the system. But if we've got excess flow from our pump and we're dumping, we're not going to actually lose any PS pressure with more clearance. And I mean, this is very much an oversimplification, but I'm hoping you're understanding what's going on here, because the one thing that I see that is a horrible mistake that a lot of people will do is we're going to put a high volume pump on. Yeah, that'll fix all of our oiling problems, no matter what. Except it doesn't. In fact, you might have just created a bunch of problems. Because now, let's say we're making 2x of flow out of our pump. Well, we still only have Y coming out for flow. Which means now we've got all kinds of bypass going on in our pump. So much so that we might actually have our 50 psi spring bottomed out and we're making 65 psi still, because it can't bypass enough volume to bring the pressure down. So then we go up to 3 thou clearance, and guess what? We're still freaking just pounding that thing full of oil, and we can't even get close to the pressure we actually want, even with stupid big clearance. So what this is doing now is that pressure is increased in the whole system. We're just bombarding the system with pressure. Well, we're only flowing so much. The pressure goes up, we're flowing a little bit more, but we're not making up for the difference that the oversupply we have out of our pump is. So what that's doing is it's forcing our pumps at a fixed speed where we can't adjust our pump. Not in most cases. If it's a dry sump, we can adjust it, but or if it's an external that has an adjustable, but again, we're adjusting the bypass valve. We're not adjusting how much oil is being pumped, because that's determined by the gears. So maybe we're getting a little bit more. So maybe we're getting Y.1 out of our system, but that's about it. So what that's really doing is we're forcing our pump to work hard because it has to, and we're robbing horsepower. Oh, whoops. So we're robbing horsepower from ourselves. Now this is just a generic example here, but a real world example that I've tested on the dyno is we had a customer engine that had a Titan wet sump pump. I mean, they're really bad to the bone pumps. They're really awesome. All full billet, crazy pumps. This was I think it was a 565 cubic inch Pontiac engine. Yeah, crazy pump. We had oil clearances where we wanted to set them based on using the weight oil we wanted to use. And that pump was making 120 PSI. Absolutely ridiculous. There's not an engine that I know of that needs 120 PSI oil pressure. I mean, the general rule of thumb is 10 PSI per 100 horsepower up to about 60, and then you don't need any more. So to have 120 PSI is absolutely ridiculous. On my personal race car engine, my car runs at 45 PSI, hot oil pressure at 520 to 540 horse, wherever it is at these days, and zero issues whatsoever. And that's even a little bit on the low side of our 10 PSI rule per 100. So to have 120 PSI was absolutely ridiculous. And granted, I mean, this engine was making, you know, what was it? It was 960 horsepower at the time. Our bearing clearances here and letting that oil out. Another one to consider is the rod side clearance. And that is this oil clearance between the connecting rod and the crankshaft journal. Because after the oil pressure gets out off of the bearing itself, there's another side right here that then controls how much oil can flow through it off of the connecting rods as well. The mains typically don't have anything that tight except for the thrust. The thrust has that. But same thing, this is another restriction to oil. And a good example of this is stock Oldsmobile. That side clearance is only 6 thousandths. So that's 3 thou a side. Most aftermarket connecting rods are all set up for 16 thousandths of oil clearance. And that's what this big Pontiac had, was 16 thou. But because we had this crazy oil pressure, we wanted to bring that down. Now this was on top of a couple of other mods, because while making 960 horsepower, one of the cylinder heads on it had not been heat treated correctly, and it ripped the rocker system out. Like a full shaft system tore out of the head, tore the threads out of the holes. So I had to come back off the dyno anyway. All that we did was we repaired the damaged head with some big certs, because the company that made the head refused to replace it. Whole other thing. But the rod side clearance here, we took and opened it up to 28 thousandths. So we added 6 thousandths per side of oil clearance. And we saw a little bit of scuffing on the skirts of the pistons, like just barely a scuff So we added a half thou of cylinder wall clearance, which, if you were paying attention in the previous video, we were talking about the short block, that opening up that clearance, you know, more risk of losing a little compression past the rings, but more or less we were doing it just to make sure that longevity-wise it didn't wear out the pistons. However, that is something worth noting for this A-B comparison on the dyno. The big thing we did was open up the rod side clearance, and when it went back on the dyno, it made 980 horsepower with 95 psi of oil pressure. The only thing that we changed that could have affected this oil pressure was the rod side clearance. And it made 20 more horsepower because of it, with a not quite 1-to-1 ratio, but pretty close. You know, a 25 psi drop and 20 horsepower from it. And even 95 is still way too much oil pressure. But at least it got down low enough where we didn't have to worry about just blowing every fitting in the system apart. But that's still way higher than we wanted it to be. But the engine ran fine. We didn't have any more problems with that cylinder head, and that's where it was going to be to give it back to the customer. And it's just pointing out that you don't need to put crazy high volume oil pumps on things if they don't need it, because really all you're doing is robbing yourself of horsepower. Or the other thing that I haven't quite touched on yet is that your oil bearing clearances, are limiting the oil that goes to them. So where else can the oil go if you've got crazy high pressure? Well, in most applications, it can go up the push rod with the lifters because it's designed to go to the head, and you can just pump all of the oil to the top end of your engine, and faster than it can drain back at high RPM, and you'll run your oil pan dry because you put a high volume oil pump on also. So this needs to be considered, and the way I would go about choosing this is you need to decide what clearances your engine needs first, and the clearances are going to be determined based on the components you're using and the type of build you're doing. If you've got a big block with a heavy crank, heavy rods, heavy pistons, you need more oil clearance. Just because those things are going to want to bend and flex more, so they're going to be moving around, and they're more likely to crush out your oil clearance, little oil barrier or oil film layer. They're more likely to crush it out and make it disappear than something with lightweight components. So you need to just figure out what clearances you're going to run first. And we'll get into it in a minute here, but the next thing is once you have your clearances, then you know what oil weight you need. Clearances determine what the oil weight is. And then those two things together should determine whether or not you need to have a high volume pump or not, based on the system as a whole. Because you can have clearances that are, just example, let's pick 3 thou. 3 thou's on the loose side. With those kinds of clearances, you should be running a heavier weight oil. But you don't need necessarily need a high volume pump, because your heavier weight oil should flow slower, helping raise pressure, and it will keep our oil film layer properly supplied, and we don't have to have a high volume pump to do it. And if we have are properly supplied and we put a high volume pump on anyway, all we're doing is turning on the bypass. Possibly to the point where it doesn't bypass enough and we run into these other high pressure problems we're talking about. If we run a thinner oil on our big clearances, it's going to flow faster, reducing pressure, in which case we probably do need a high volume pump to then bring the flow rate up enough to bring our pressure back and keep our layer properly supplied. But that means we run into the other issue of we need to make sure we have enough oil in our oil pan to keep the pump supplied so that we don't suck air and run dry. Oil weight, viscosity, choosing this for an engine. You know what? I'm gonna throw right in brand along with this. That if you go on the internet and ask what oil should I be running and what brand, I don't know, it's such a ridiculous question. If you're asking that, you do not properly understand what's happening with an oiling system. It is you're asking the wrong questions. We need to look at this based, as far as brand is concerned, I don't care. The big thing you should be asking yourself is, are you having a problem with the current oil you've been using? If the answer is no, then you have absolutely no reason to be thinking about switching. It's just, you're talking a vanity question at that point there. It doesn't freaking matter. So, we care about the oil weight and viscosity. So, typical stuff that modern cars, we're getting into what, OW20 stuff? Ridiculously thin. Very thin oil. Pretty much normal stuff is more like a 530, you got maybe a 1040, and then of course 2050. But the difference is your 2050 is thick. So if we just generically label them as, we got very thin, medium, and thick. And maybe these are not the right way to label this, because what we're describing here is more with the viscosity about how does it flow. And that should really be measured as a flow from fast to slow. And like we were just talking about with our oiling system, flow versus pressure, our oil weight, viscosity, has a huge effect on that, because if we want to talk about it like an extreme, how hard is it to run water through a pump versus molasses? We're talking an extreme comparison there, but it should help you visualize that the amount of stuff you're getting through that pump is going to be wildly different between those two materials. And our oil weights is how it's advertised, but really we're talking about viscosity between them. And it's just whether it flows really fast or it flows slow. Now, our number 2 number here of the weight actually refers to kind of like a tensile strength, the amount of pressure that the oil can support. So when we look at this versus our oil barrier layer, so if we go oil layer thickness, it's thin to thick, which makes our talking about the way it flows more of a closer reference there. So or 20 can support a smaller bearing clearance than a 2050 can, and a 2050 can support a pretty big bearing clearance versus a 20. And that's because of how fast it's flowing. If it flows slower, it stays, it can build up, be thicker, versus if it's really thin, it's just runny, like water, or even thinner with some of these oils or whatever. It's like it's just going to shed off. Like you're going to have a thinner bearing clearance to hold it there and make it do its job properly. So this is where we come into clearances. If I got building an engine and let's say just a generic middle of the ground, what I have done lots of times and know works well is we're going to have, say, a 3 thou main clearance with 2.5 on the rods. So mains, rods, that's the oil clearance I'm choosing to run. For that, I know what's going to work really good for that is a 10W40, because we got a little bit bigger on the main. 2.5 is, in the upper side of what you would typically normally do for a rod. So we're to the high middle ground of what we want to run. We're going to go to a high middle with our oil weight. We know we're gonna flow decent, like in the middle. We got 40s giving us good oil support so we can handle the larger clearances, and that's going to be a great choice of oil weight for the clearances. Now, if I ended up building an engine and we ended up at, say, 2.2 on the mains and a little under 2 with 1.8 on the rods, that's on the tight side. Like tighter than I would typically ever choose to run a normal V8 kind of a thing. However, it can be set up to run properly. But with those clearances, and you stuck 2050 in there, that engine is blowing up. Almost guaranteed to blow up, because the oil will never flow fast enough to properly support the oil layer. Like it might have the oil layer there, but it's going to be slow enough where you're going to cook the oil. It won't flow fast enough to cool everything down properly. So you also got to think about your oil like the radiator system on your car. It's not just lubricating, it's also cooling. So 2050, absolutely the wrong choice on there. Probably going to damage your engine because of it. So we're probably going to look at a 530 for something like that. If we've got something set up where we're running a high volume pump and we're wanting to just cycle the oil really quickly, might even go to the 020, because we're actually pumping it through the engine fast enough, provided we don't run our pan dry, like we talked about before, that it will do a better job cooling the components by running the thinner oil, because you're cycling it out fast enough. But if we don't have those components designed that way in place, 530 is a much better choice for that. On the flip side, I have actually had some engines that ended up at 4.5 on the mains with over 3 on the rods, and this is 2050 all day. I wouldn't do anything other than 2050 and something with that big oil clearances. And being as they're so big, this is probably something where we might need to be also planning to have that high volume pump along with it. But if they were, say, 2050, say we had 3.5 and like 2.8, kind of in between, and we still wanted to go with the 2050, then we'd probably be just fine with a standard volume pump and not have any issues. But this is where we're getting into that clearances on your engine decide everything. And it is worth noting that when we start talking about overhead cam stuff, where you got lots of buckets, lifters, little parts, all of the clearances in those overhead cam heads are all pretty tight. All those engines were designed around like a 530 on the heavy side. Most everything's gonna be a 520 or an 020 with those engines. And it's because of all of the little parts on top. You stick a heavyweight oil in those engines, it almost won't flow the oil out of those parts and will absolutely cook them and destroy the engine. So with that being considered, you need to take that into account, that you can't have crazy oil clearances on your crankshaft, because you need the thinner oil for your cylinder head, and therefore you better be sticking to a tighter oil clearance on your crank and rods, because you have to run that lighter weight oil. And if you run the thin oil with big clearances, even if you crank up to a high volume pump, you might not be able to build the pressure properly for your top end, because you're just dumping the oil as fast as it'll flow out of the bottom end. And it might be okay pressure wise at the crank, but you might not be getting that same pressure at the top end, because it's going through a lot of other restrictions on the way to get there. Plus, then there's just so many small openings up there, the pressure drop is going to be pretty big. Now, you can't figure out any of that unless you measure your bearing clearances. And I mean measure them correctly so that you know what they are. So we got our cap and our block. This is our opening. But to figure out what the bearing clearance is, we first need to measure the journal on our crankshaft. Always measure it in 2 directions, so that if there's any out of round, you can factor that in. So let's say this is a 2.5 inch main. So we come up with it's not going to be 5 though, it'll be 2, 4, 99, 5 or whatever probably. So that's probably middle of spec, because it'll be 2.5 to 2.4999 or 990. So that's dead center of spec. Well, we could probably end up with this when we actually measure our crank. It might have been 2.4998 one way and 2.4996 another way. Well, we'd average those out and we call that crank journal 2.4997. That's the number we actually want to look for. And we're going to measure that on every single journal of our crankshaft to make sure that we know what each individual journal is. You never measure just one and assume that they're all the same, because they're not. Even on a really good ground crank, there's still going to be a few tenths variation. Now, when we get over to our mains, our main bore here should have been set when we had our line home done. So now we've got to put our bearings in. And we're going to torque everything up. And then I want to measure a bearing like this. I mean, the main is the same as how I'm going to measure the rod. I'm going to start with doing these 2 measurements. And let's say that I got 2.50, I don't know, 17 in one direction, and I got 2.5012 in another direction. Now that's a half a thou off. I'm going to use this as an example because that is very much a measurement you might come up with, because as we touched on previously in a different video, is bearings are not even and round. They're actually shaped kind of like this, where they're thicker at the bottom than they are up on the sides. And that is due to the running stresses trying to separate these parts, and by trying to pull up, they're stretching this way, it makes it pull in. So they're designed to be thinner at the parting line so that it doesn't pinch in on your crank journal. So to end up with two staggered numbers like this is not uncommon. You also got to factor in the variation of the bearing manufacturer themselves. If you've been building engines very long, there's definitely a hierarchy to the quality based on the brand. Sealed Power Speed Pro, you're probably going to need 3 sets to make one good set that's consistent, because the sizing is all over the place. If you're just putting a stalker together, probably just fine. It doesn't matter. You won't have consistent oil clearance. Cleveite, ACL, they're usually pretty good. There's, a few tenths variation here and there, like enough where the tolerances stack up, or maybe you gotta, swap one bearing half with another to even out your sizes, but they'll usually be pretty good. But they're not, and they should be pretty close to what Target is actually supposed to be with those brands. One that I've used a lot of is King. King bearings, as far as consistency across the set, very accurate, more accurate than anybody else in my opinion. However, the size across that set can vary by thousandths. You can have the same part number out of different boxes. The tolerance of each box is going to be super consistent with everything in that box. But box to box on the same part number will have variation. So just kind of you're gonna get what you get with bearings. I don't know, the quality is, I'd say the quality is good for ACL, Cleveite, King, ones like those. It's just you have a little bit of just variation, nuances between them. Anyway, circling back. So we're going to measure these two diagonals, and I'm going to average these. So this comes out to you know what? I'm gonna change this to a 1 just to make it easier on us. So it's gonna be 2.501 is the middle. And then I'm gonna take another measurement in the vertical direction. And let's say that comes out at 2.5 0.012. Now I'm going to average both of these. 2.5013. That is our true size, or what my method of measuring bearing clearance is. This is the true size because it's our average of averaging. And like we talked about in a previous video, this zone right here, we don't care what any of that measures because it's going to measure big. It's going to be like 2.503 or something ridiculously big compared to the rest of it. Doesn't matter. Our loads are all, you know, even a V, we're talking our loads are going like this. We're only putting all of the load into that area. We're not loading it side to side at all. Doesn't matter. And when it's running, that stuff's going to pull in, so we can't even measure that correctly in a assembly scenario as it is. So when it's running, this number will get smaller, our red vertical number will get bigger, and it's going to average out into the middle of that again anyway. So this is how I'm measuring my bearing clearance now that we've got 25013, and then we'll subtract our journal, that specific journal that goes in that specific bearing, 2.4997, and we're going to end up with 1.6. So that's a really tight clearance. I made up these numbers as we went. So that's going to be our average bearing clearance. This is the number that if I'm blueprinting an engine, this is what the number I'm writing down is. This is the number I'm basing all of my oil system choices off of. And my very first choice with this bearing clearance, if it came up, was we're going to change our bearing to an X bearing. Because our X bearing should give us a +1 thou. And I like 2.6 a hell of a lot better than 1.6 for a typical V8 build. And just to drive the point home about why I take the two diagonals and average them instead of doing a vertical measurement and a horizontal measurement at the parting line, is because with that big number, we would have averaged these two out, and it would have been 2.5. See, 189, like 2.1 as our average. And you can see we're almost an entire thou off. And that number's reading big only because of the way our bearing is shaped. And that's not a true oil clearance. And if we were basing it off of that number instead of that number, we're going to think we have a lot more oil clearance than we actually do, because down here we wouldn't have ended up with 1.6. We'd ended up with 2.4, which I would have been more than willing to accept as that's a good oil clearance. But no, it's not, because it's not a good measurement, because we're so far into the taper on our bearing. It's just, it's not good. That's why you do the diagonals and you average them. You're going to get a way more consistent number for getting a true bearing clearance. And should go without saying that these bearing clearances are measured with a micrometer and a dial bore gauge. Do not rely on Plastigauge. It is better than nothing, but Plastigauge can be very inconsistent. And here you're measuring the hard parts with a good gauge. It's not lying to you. Plastigauge can lie to you. And if you don't put it consistently exactly in the same place every time, it's going to be different. Plastigauge is typically only going to have you, or people who are using it anyway, are only going to measure the vertical oil clearance, which then they're only getting this number, which then when we compare to that number is going to give us a number that's not true either, because on the diagonals, I mean, maybe it's consistent with the vertical, maybe it's not. But we don't know because it wasn't measured and checked. I mean, the bearing could get absolutely huge over here and you're only checking it there with Plastigauge. You have no idea. You got way more clearance, or maybe you got way less clearance than you actually think. So Plastigauge is just not a good way to go about it. If you are having your engine built at a machine shop, have them do this. Have them measure the stuff so that you know and they know and you can make a proper decision on your oiling system because of the clearances you have. Or if you have a problem where it's too tight, you can take care of that now instead of having no clue and possibly running into an issue later. I know the big argument is for crate engines these days. It's just, it's cheaper, it's easier, blah, 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 whatever. Well, crate engines have warranty departments. Why do they have warranty departments? Because pretty much what they're doing is they're popping one bearing cap off, sticking a feeler gauge in it and torquing it back down and making sure the crank doesn't turn. And they pull it back out and the crank turns, they call it good enough. So if you're buying a crate engine, you don't know what clearances are. Yeah, most of V8 clearances there, they can be as tight as 1 thou and they can be as loose as 3. Well, we've already established when talking about this that that is a big difference in the choice of oil you want to run to have that engine properly supported by the oil. And you don't know when you're getting a crank build or a crate engine build because they probably never even checked it. That's why I'm a big proponent for using a proper machine shop that knows what the hell they're doing and can do a quality engine build. Or there's no reason you can't do these things if you're assembling the engine yourself at home. You can do this whole process there. You know, it may not be the best style bore gauge, but you know what? There's plenty of them that you can find that are like $100. And it's way, way better than plastic gauge because you can measure the diagonals, you can measure the, and you can do it as quick as, yep, write down the size. Yep, write down the size. Write down the size, do this quick little math, and you're done. You know what the number is. And you can have a set of micrometers, or you can have if your crank was ground, it should come back with a tag from your machinist that shows you what slices it is. Now, not everybody might be giving you the exact size on every single journal, but if the crank grinder was any good, it should be plus minus a tenth or two at the most. So it's something you can go off of, or you can just have your machinist measure it and write down the numbers. Preferably though, the micrometer you use to measure the crank is the micrometer you use to set your dial bore gauge. And then you know it actually, the number doesn't matter because you're literally just measuring the clearance right from the get-go. So whether the number is 2.4 or 2.8 or it's ABC, it doesn't matter because whatever it indicates is what the clearance it is. Hopefully this video helped bring you a little bit of education on oiling systems and bearing clearances, and just do not be the person that goes onto a forum and asks, what weight oil am I supposed to be running? Because if you don't know what the clearances are, you are wasting your time asking the internet because it's like, your oil should be oranges. Like, that's as good an answer as anybody else is going to give you. Just, yeah. Take the time, do things the right way, and the more time and effort you put in to doing this stuff and the better you know your engine, the better engine you're going to have when it's all said and done.